Another algorithm for working out or finding a minimum spanning tree is called Kruskals algorithm. Again, it's another greedy type algorithm. It's quite similar to Prim's algorithm, but it's, I think, conceptually a little bit easier in the way it goes through, and it's, I think, also a little bit easier to program. I don't have any of these in the notes, but I thought we would go through it since it is such a nice thing. So again, here is our weighted graph, and the trick with Kruskals algorithm is actually to write down all the edges in order of their weights. All the edges of weight 1 are DF, EG, BI, CJ, BE, GI. Doesn't matter which order you write them down. I've just put them down in this particular case in a random order. The next one is AH, weight 2, and HF through to IJ with the various increasing weights. So list of the edges in order of ascending weight. So what we do is we basically work our way down the list from top to bottom, and we just add an edge as we come to it, provided we're avoiding cycles. Now, this means that it's possible that intermediate steps might be disconnected. Okay, so the main thing is that we're just avoiding cycles, which is like a tree. Remember, trees are connected, and in Prim's algorithm, we keep things connected. In this algorithm, Kruskals algorithm, we don't need to keep things connected. So let's go through and see what happens. So first in the list is DF. Where's DF? DF is here. So we'll add that in. It's, again, worth writing down as we go through which ones we're adding in. EG, we ask ourselves, can I add EG in without creating a cycle? And the answer is pretty clearly yes. You can see why this is a greedy algorithm, because since we've got everything listed out in order of the weights, we're adding the greediest thing we can do at each step. We want to find a minimum spanning tree. We just look for the minimum weighted edges that we can add in. And it turns out that this way of doing things does work. Okay, BI. Okay, B to I, we can certainly add that in. Okay, C to J, yes, we can add that in with one each. What's next? B to E. Can we add in B to E? Yes. Now, notice at this stage, everything is disconnected as far as the spanning tree goes. So B to E, yep, we can add that in. Still disconnected. G to I, weight 1, that's the smallest of the things left. G to I, no, we can't add that in because this would create a cycle. So we wouldn't be avoiding a cycle. So we can't put in G to I. Can we put in A to H? There's A to H there. Yes, we can, because if we put in it still avoids a cycle. A to H. H to F. Yes, we can add that in. No cycles created, so that's fine. That's worth 3. B to J. B to J. Yes, we can add that in. No cycle was created. That's worth 3. A to D. A to D. No, that would create a cycle, so we'll skip over that. F to G. Yes, we can add that in. That just goes in there. And that was worth 4. A to B. If we put in A to B, that would create a cycle, so no good. D2E, D2E would again create a cycle, so no good. B to C would create a cycle. H to Y would also create a cycle, and I to J would also create a cycle. Actually, we really didn't need to check these because 10 vertices, we know that the minimum spanning tree will have 10 minus 1 equals 9 edges. How many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know we could have stopped there. And in fact, looking at this, we can see we can stop because all the vertices have been covered. And again, 4, 7, 10, 12, 13, 14, 15, 16, 17. Total weight of 17. And notice that this is a different spanning tree to the one we got from Prim's algorithm. That's because there are several different spanning trees in here, and different algorithms sometimes give you different results. So there's one, Prim's algorithm. Put it there. The section's the same, that's the same, but then around here is a little bit different in the two. And also, if we had ordered these differently, so there was, I just chose this ordering for the edges of weight 1, but if we had ordered them in a different fashion and then ordered them in a different fashion for the 3s, then again we would have gotten a different minimum spanning tree. So again, another greedy thing. This one's really obviously greedy because it's really doing the smallest edge at each step. Whereas you notice, while Prim's is also greedy, we went 1, 1, 3, then so that was bigger than those, but then we got a small one, then big one, small one, and so on. Here it was always choose the smallest ones, and then they're increasing as we go through. Right, so that was Kruskals' algorithm.